Hi, for today's video, we're going to go through all the problems for the homework 6. And let's take a look at the first problem. In this problem, we have a glass tube placed in a flowing stream. In this problem, we know the velocity of the stream is 6.6 meters per second. We also know the g, the gravitational acceleration, it equals to 9.81 meter per second square. And in this problem, we want to know how high will the water rise, which is the h. So to solve this problem, first we need to write down the Bernoulli equation for the stagnation point and with the point A. So for the Bernoulli equation for the stagnation point, so it's depth plus the pressure head, which is Ps over gamma, plus the velocity head is Vs squared over 2g. Similarly, for the point A, it equals to depth z1 plus p1 over gamma plus v1 squared over 2g. So if we set the data as a level at the stagnation point, we call the distance, the depth from the water level to the datum, we call it d. Then we can know that the depth for the stagnation point it equals to 0 because it's at the same level as the datum. And Ps, the pressure at this point, is a hydrostatic force. It equals to the gamma times h plus d. And then, because it's a stagnation point, at this point, the velocity it equals to 0. Therefore, the Vs it equals to 0. And let's take a look at the points at point A here. So the z1, it equals to this distance, is d. And P1, because it's open to the atmosphere, so the relative atmospheric pressure at this point, it equals to 0. And V1, it should equals to the velocity of this flowing stream, it equals to 6.6. So after we bring all these values to the Bernoulli equation, then we can get on the left hand side it equals to 0 plus h plus d plus Vs equals to 0. So it's 0, z1 is d plus 0 plus 6.6 squared divided by 2g. And g is 9.81 and d can be cancelled here. So we can get h it equals to 6.6 squared over 2 times 9.81. Then we can get h equals to 2.22 meter. So this is a result for the first problem. Now let's move on to the second problem. In the second problem, we have the flow of water over the surface. We have three scenarios listed here. And we also know the depth of water at section D is the same, and the mean velocity is the same as well. So we want to compare the pressure at point A, B, and C. So the first two scenario, it has a curvature. So let's write down the pressure at point A and point B first. So for the first scenario, which is listed here, the pressure A, it equals to the static pressure minus the curvature pressure, the pressure caused by the curvature. And for the second scenario, the pressure at point B, it equals to the static pressure plus the pressure caused by the curvature. And the last scenario, there is no curvature. So the pressure at point C, it equals to the static pressure. So based on these three equations, we know the pressure at point B larger than the pressure at point C, larger than the pressure at point A. So in this problem, we should choose the option B. So for problem 3, we know there is a two-dimensional flow. We know the velocity component in x and y. We also know the c is a constant. So the problem asks us to determine if this flow is irrotational or not. So in other words, to determine if this flow is irrotational based on the definition, the partial derivative of v with respect to x minus the partial derivative of u with respect to y should equals to 0. So actually this problem asks us to determine the value of this part and compare this value with 0 to determine if there's rotational flow or not. So to solve this problem, first let's calculate the first part, which is partial derivative of v with respect to x. We know the v it equals to cy over x squared plus y squared. So if we rearrange this part, it should equals to cy times the x squared plus y squared to the power of minus 1. Then we can use the derivative rule for the product. So it should, because it's respect to x, so it should equals to cy times minus 1 times x squared plus y squared to the power of minus 2. Then times x is here, so times 2x. Then we plus the take derivative for cy because the c is a constant, and this part should equals to 0. So 0 times anything, it will be 0. So the result for the second part will be 0. So after we reorganize this part, it should equals to minus 2 times c times xy over x squared plus y squared to the power of 2. Similarly, we can calculate the partial derivative of u with respect to y. It equals to cx over x squared plus y squared. So it equals to partial derivative to the power with respect to y equals to cx times x squared plus y squared. Then we do the same thing as we did in the first part. So after we finish this calculation, we can find it equals to 2 minus 2 times c times xy over x squared plus y squared to the power of 2. Then we find partial derivative of v over x minus the partial derivative of u with respect to y. It equals to 0. Therefore, we know that this flow is the irrotational flow. Now let's take a look at the problem 4. In this problem, there is a pipe. We know its diameter is 21 inches. We can convert it into feet. We also know the velocity in this pipe. It equals to 10 feet per second. We also know the 1 cubic feet per second equals to 449 gallons per minute. We need to determine the flow rate in this pipe. So to solve this problem, we need to use equation. The flow rate equals to the velocity times the area. And we know the area equals to 1/3 times pi times d squared. The velocity is 10 feet per second. And we know the diameter here is 21 over 12 square. So after we do a simple calculation, we know the flow rate equals to 24.05. The unit is cubic feet per second. And we also want to know the flow rate in gallon per minute. So we should use Q equals to 24.05 times 449. So it should equals to 10,799.71 is gallon per minute. So the result for problem 6 is this two. Now let's take a look at the problem 5. In this problem, there is a channel used to transport the water. We know the width of the channel is 1.2 meter. We also know the vertical depth of water in this channel is 1 meter. And the angle of this channel is 30 degrees. It also provides us the velocity. It equals to y to the power of 1/3 meter per second, which means the velocity is changing in y-axis. So because of that, we use the integration to calculate the flow rate. So before we calculate the flow rate, we need to determine the depth of water in y-axis first. Because we know the angle here is 30 degrees. This line is perpendicular with the vertical line. And the line of the depth, the D here, is perpendicular with this line. Therefore, the angle, these two angles should be the same. We know this angle is equals to 30 degrees. So the angle here should also equals to 30 degrees. And we already know the h is equals to 1 meter. So the D should equals to h times the cosine theta. And if we write a right triangular, we could find this is 1, 2, this is the square root of 3. This is the theta. So from that, we can know the cosine theta, it equals to square root of 3 over 2, right? So the D should equals to 1 times square root of 3 over 2. It equals to this. Then in the next step, we can calculate the flow rate. The flow rate should equals to the integral from 0 to D is to this point. From this point to this point, right? So it equals to the velocity times dA. A is area. And we know the velocity is equals to y to the power of 1/3 and A equals to B times y. Okay, so because we know the B is a constant, so we can put it outside. So the equation is equals to B times integral from 0 to square root 3 over 2 times y to the power of 1/3 dy, right? Based on the integration rule, it equals to B times 3/4 times y to the power of 4/3 from 0 to square root of 3 over 2. Then we can bring the value to this equation. The B is 1.2 times 3/4 times square root of 3 over 2 to the power of 4/3 minus 0. Then we can calculate the value of the flow rate. It equals to 0.743 cubic meter per second. So this is a result for the problem 5. Now let's take a look at the last problem. In the last problem, the water from a pipe is diverted into a weight tank for exactly 1 minute. So the 1 minute equals to 60 seconds. We also know the increased weight of the tank is 80 kilonewton. It equals to 80,000 newton. And we also know the temperature of the water is 20 Celsius degree. So based on the information provided on the table 8.5, we know the specific weight of water is 2,790 Newton per cubic meter. So in this problem, we need to determine the flow rate. So we know the weight, it equals to mass times G. And we know the mass, it equals to the volume times the density, right? So if we bring these two values together, we can get the weight, it equals to the volume times the rho density times the G. The rho G is gamma, right? So the weight, it equals to volume times gamma. Then we know the volume should equals to weight over gamma. So this is the first step. We use weight and gamma to represent the volume. And then in the second step, we can calculate the flow rate. The flow rate is equals to the volume of water changes in a specific time. So we can bring this value to this equation to this one. So it should equals to the weight over gamma times the delta T. And we know the weight is 80,000 Newton. Gamma is 9,790 Newton per cubic meter times the delta T is 60 seconds. So after we calculate this equation, it equals to 0.136. The unit is cubic meter per second. So in this problem, we should pay attention to the unit conversion, okay? So here's the result for the last problem.